Hello everyone, I'm Bori. I'm going to present our recent work, Efficient Zero-Knowledge Arguments for Paillier Cryptosystem. This is a joint work with Wang Fellow, my supervisor Manhao Ou, Rupeng Yang, Haiyang Xue, and Li Chunli. So election happens everywhere around the world, and many different statistics or analyses are reported by media or poster companies based on various of features of the voters. And let's take a concrete example here. For example, exit polls by age. Suppose there are 4 candidates in a voting campaign, and each voter can vote for only one candidate of his choice. And a party P2, which may be CNN, does a telephone interview for the potential voters of their preferences towards different candidates. So it collects this table of data through the telephone interview. And it wants to figure out the age group that favors each candidate. So it may seek collaboration from another party P2. So here, P2, which may be the AT&T company, who collects its clients' ages. And to finish this analysis, both of them want to complete it securely without revealing their raw data to each other. So Paillier is a prominent solution for providing additive homomorphism property and can be used to secure this two-party data aggregation scenario here. So more specifically in this example, P1 will first pass all the records belonging to the same entity into one message. For example, for the first entity, it will first convert this table using binary record 0 or 1 to denote the preferences. So it will use 0 to denote that this entity does not vote for that candidate. Otherwise, it will use a 1. Then it will pack all these records towards the same entity into one message. And this message should hold some structures. So firstly, the message is divided into several slots. And secondly, in each slot, the binary record is only inserted in the last bit, where others should keep 0, so that we can reserve them for future computation in each slot. So after P1 structures or messages according to different entities, it will use Paillier to encrypt them and sends the ciphertext to P2. Then P2 will attach the corresponding weights, which denote their ages on the ciphertext, compute the summation, and send the result back. When receiving the summation result, P1 will decrypt and pass it to get the age group that supports each candidate. But however, a malicious P1 may deviate from the message structure and steal data from P2 after passing the final result. For example, in the second slot of the second message, a malicious P1 may insert the bit 1 in the higher position of this slot. So after passing the final result, we can see that the corresponding weight W2 will be observed in the higher bit of the final result, which means that data from P2 can be easily stolen by deviating the message structure. So to prevent such a malicious P1, we could require it to provide a zero-knowledge proof along with the ciphertext and send them both together to P2. To be more specifically, P1 is required to prove that firstly, each ciphertext is correct Paillier encryption of the message, and secondly, each message should hold correct structures. That is, each message should be divided into several slots, and the binary record can be only inserted in the last bit of each slot, while others should keep 0. That is, we are required to prove the relation R star displayed in our right-hand side. There are actually multiple zero-knowledge proof constructions proposed for Paillier, but however, none of them focus on proving Paillier messages with structures, and their costs are linear to the number of entities. One may consider using existing sublinear proof system in our scenario, but it is also impractical. So the reason lies in that it requires to generate a circuit over a prime field to represent statements related to Paillier. But however, Paillier works under modular a composite number n square, and this will result in feasible circuit size and costs. So to design a zero-knowledge proof that can be useful in our considered scenario, consider that one P1 may collaborate with multiple P2s for different kinds of analysis, and the analysis may include thousands or even more messages at a time. So our aim is to construct a zero-knowledge proof that can support batch proof and verification, has sublinear proof size, low verification cost, and can be reusable. So it goes to our solution. So our underlying protocol is BCC plus 16. In this paper, it constructs an efficient zero-knowledge proof with a series of linear and multiplication constraints as inputs. So to prove our relation R star, our aim is transferred into constructing a constraint system to represent this relation R star here. Then we can reuse the technique proposed in BCC plus 16 to derive an efficient zero-knowledge proof for our constraints. But what I want to emphasize is that our constraint system should work under modular a composite number n square here, because we are using Paillier in our aggregation scenario. So we'll start by constructing constraints for correct Paillier encryption. So the Paillier encryption can be rewritten as this, and we can say that the first part is already a linear constraint. Next, we'll construct constraints for representing R to the power of n here. So here we'll use an example to illustrate our approach. Suppose n equals to 11, and we first write down its binary representation as this. It is 1011. Then according to the number of its composition bits here, we square R for 3 times, so that we can get R to the power of 2, R to the power of 4, and R to the power of 8. Next, we multiply some of them according to the ones in the decomposition bits. That is, we first multiply R and R to the power of 2. We get R to the power of 3. Then we multiply R to the power of 3 and R to the power of 8. And we can get R to the power of 11, which is the final result that we want here. So let alpha denote the number of binary decomposition bits of n, and beta denote the Hamming weight of n. So following our steps, we can use alpha plus beta minus 2 multiplication constraints to represent R to the power of n here. To sum them up, we can use this many of linear and multiplication constraints to represent one correct Paillier encryption corresponding to ciphertext C, message M using randomness R here. And we denote these constraints by this notation for the one correct Paillier encryption. And next, we are going to prove that one message is binary. We start by using one multiplication constraint as this. That is, m times m minus 1 equals to 0. But however, it does not work here. The reason is that our constraints are under modular a composite integer, and there may exist 2 other non-trivial rules here that also satisfy this constraint, that they are x and y here, and they are quite large. So to prevent the prover from using these non-trivial roots, we let the verifier to verify the range of the message. To be more specifically, we first let the prover to first choose a randomness R prime from a relatively small range compared with the non-trivial roots. And this randomness will be used to hide the message later. Then the verifier can choose a random challenge bit L. Then the verifier is required to compute the linear combination with the message, and the result, we denote it as L prime and send the result back to the verifier. Since the randomness is relatively small compared with the non-trivial roots, so by checking the range of the combination result, if it is not that large, then the verifier can be convinced that the prover didn't use any non-trivial roots in its computation. But here we still have 1/2 probability to have a cheating prover. So we repeat this whole process for kappa times to reduce the soundness error. And we can extend to prove that polynomially messages that are all binary. That is, we use the same constraints on each of the message to prove that each of the message is a binary. Then we are going to prove that polynomially messages hold correct structures. That is, each message is divided into several slots, and the binary bit is only inserted in the last bit of each slot, and will start by 2 slots in each message here. So for each binary record, we use the same constraints to prove that they are all binary. Then for each message, we use one linear constraint to prove that these 2 inserted binary records are located in the correct position. Next, we can extend to prove more slots. For example, we'll have 64 slots in one message. And here we want to use the same technique, but by covering more binary records in the linear constraint of each message. But however, this does not work again. The reason is that our technique for proving a binary bit can only work if these bits are fixed. And our analysis is that only if the message satisfies this length requirement, then given its Paillier ciphertext, its binary representation bits can be fixed. But right now, the message has more slots. That is, each message has 64 slots, and each slot consists of 32 bits. So the message right now does not satisfy this length requirement. Therefore, our technique cannot be reused anymore here. So to fix this problem, we construct auxiliary messages using binary records to be proved to make the auxiliary message satisfy the above length requirement. That is, the auxiliary message length cannot be that long. So here we use the binary records from every 15 messages to construct one auxiliary message. But this specific number can be changed due to different parameter settings here. Then we use Paillier encryption to commit these auxiliary messages. So based on our previous analysis, right now we can fix all these binary records here. Then after this, we reuse our technique as before to prove that all these binary records are actually binary and they are located in correct positions of each message. So to put them all together, we can use these constraints to represent our relation R star. That is, we can prove that polynomially messages that are correct Paillier encryption and together the corresponding plaintexts hold specific structures as we've explained before. And for the performance of our system, we examine it under 2 sets of parameters. And for the 2-party data aggregation scenario we considered, we can see that with proving 800 Paillier messages at a time, the proof size is less than 2 or 4 megabytes under different parameters. And besides, we can see that the required verification time is also very small. And our system can achieve sublinear proof size. That is, with proving more messages at a time, the proof size for each binary record will be reduced. So if we prove more messages at a time, the proof size for each binary record can be even less than the encryption size for each binary bit. We also compare ours with using an or proof. So compared with using an or proof, our system also gains benefits in both proof size and the verification time when we prove hundreds or more messages at a time, which suits the aggregation scenario in practice well. So to be more specifically to use all proof, P1 should first use Paillier to encrypt each binary record, then prove that it is 0 or 1 using a standard OR proof. And when proving 800 messages at a time, we can see that ours is 19 times or 27 times smaller in the proof size and 1.7 or 4 times faster in verification with under different parameters. So in conclusion, our work derive an efficient zero-knowledge proof for different structures in Paillier cryptosystem, which supports batch proof and verification while achieving sublinear proof size, low verification cost, and can be reused. The core of our work is actually a constraint system under modular A composite number. And our core technique is general and can be extended to derive different kinds of proofs over Paillier. For example, we can construct an equality proof for sum of records. That is, we can prove that there are at most 2 ones in each voter's preference. And such requirement can be observed in like plurality at large elections, which are held in many regions around the world. And also we can derive a range proof, that is to prove that there are more than T1s in the records towards the same unit. And this kind of requirement can be used to prevent the weight leakage from the final result. And more properties for Paillier can also be proved using our technique, and more details are reported in our paper. Thank you.